In this video, I will be discussing assignment 4 from 218 in 2020. So in the first question, they ask you to use the definition of a limit to prove this limit over here. And it also says that you may use the following statement, which is over here, in your proof. Now, please note that the statement that is actually given to us is a conditional statement, meaning something needs to be satisfied before something else holds. Now, in our case, our condition is this part. And what holds, or the statement, is this part over here. So if we want to use this statement, the condition has to hold. Now, as any question where they ask you to prove the limit, you always take the absolute value of fx, y, minus L. Now, our fx is over here, or our fxy, and this is, in our case, our L. So if we take the absolute value of cos squared of 2x squared plus 3y squared minus 1, by trigonometric identities, this is equal to the absolute value of negative sine squared 2x squared plus 3y squared. Now, because this is the absolute value, the negative falls away. And because I want to use the properties of sine, I'm going to split this sine squared into a sine multiplied by a sine. That's why I don't get rid of the absolute value, even though I know that sine squared is positive. So this, I'm just going to split up into 2. So the absolute value of sine 2x squared plus 3y squared multiplied by itself. And now I can use the property that the absolute value of sine of any angle is less than or equal to 1. So this can be less than or equal to, now I'm just going to use it for one of these terms that are multiplying, not both of them. So this will just reduce to the absolute value of sine 2x squared plus 3y squared. And this kind of looks like something in our statement over here. It kind of looks like this. But in order to use our statement, the condition needs to be satisfied. So let's state there exists a delta 1 such that this is true. The norm of xy minus 0 is less than delta 1. Then I can say that the absolute value of sine of 2x squared plus 3y squared, this will just be equal to sine of 2x squared plus 3y squared. And the reason for that is, now I'll just use a different color. It is this side of the equation, or this side of the inequality, sorry. So let's call it star, a red star. And then we can say, well, this is less than or equal to 2x squared plus 3y squared. And this comes from the other part, the other side. So this side, let's call this a heart. And now this kind of reminds us, this helps us get to something of a norm. Now this can be less than or equal 3x squared plus 3y squared. And the reason for that is because x squared is positive. And now I get back to basically writing down the definition of a limit. So the first thing we do is we say fix epsilon to be greater than 0. Now you can split this up into 2 deltas like I'm going to do, or you can just do it in your minimum bracket. Now I'll say let delta 2 be equal to the square root of epsilon over 3. Now, where does that come from? Well, it's basically if we think we want this to be less than epsilon in such a way. And that's kind of, oh, sorry, I missed a step. This should be equal to 3 and then the norm, because it's easier to see it from there. This will be the norm squared, and we want this to be less than epsilon. not that one. Well, it's essentially the same, but just so how can we, if this is delta, how can we maneuver it so that this is strictly less than epsilon? And now we have to pick and make our epsilon in such a way that our condition still holds. So what I'll say is let delta, now you can call it delta star, you just have to distinguish between the three deltas, be equal to the minimum of delta 1 and delta 2. And this means that delta is less than or equal to delta 1 and delta is less than or equal to delta 2. So that if we make the assumption that the norm between xy and 0 is less than delta, then the norm will automatically be less than delta 1 as well as less than delta 2. This is and. So now we can say fxy minus L, this has been shown to be less than or equal to 3 times the norm xy minus 0, 0 squared, and let's call that, for instance, A. And A only holds if our condition holds, and by this statement over here, our condition holds, so A must hold. And then we can call this B, we can call this B, so that our fx y minus L will be less than 3 delta 2 squared, strictly less than. And this we can say is equal to 3, and then we substitute in the value of delta 2, which is the square root of epsilon over 3 squared. And this is just equal to epsilon. Now to finish the proof, you have to say, since this holds for all epsilon greater than 0, by definition of a limit, we know that the limit as xy tends to 0 is equal to L. For question 2, it asks us to compute the limit or prove that the limit does not exist. Now please note, if we ask you to prove that the limit does not exist, that's usually what you have to do. So a question like this, it's usually to prove that the limit does not exist. And the way in which we do that is we use theorem, I just want to get the number. We use theorem 45, which I know it's a very long theorem, but it basically just says if we pick different paths and these paths don't give us the same limit, then the limit does not exist. So you might find 4 paths that give you the same limit. Usually the axes don't always work, so you're going to have to get a little bit more creative. And the only condition for your paths are they have to be continuous. So you can't, for instance, pick 1 over t. And they also have to go through the point 0, 0 at some point, but not be 0 at all of the points. So for instance, I'm just going to pick, let's say I pick a path, I'll call it, let's say R1, such that it is equal to, say, 0t. Now, it will be pretty obvious that, okay, I'm not dividing by 0, but this will be 0, because if this is my f of t, f of xy, then this would imply that f of r1 of t will be 0, so I don't even have to take the limit. But if I pick another one, let's say r2, such that it is tt, then f of r2 of t will be equal to t cubed over t cubed plus 2t cubed. And this is equal to a third. And the limit of both of these constants are just constants. So we can already say that the limit as t approaches 0 of f of r1 of t, this is not equal to the limit as t approaches 0 from f of r2 of t. So then we can say by theorem 45, this limit does not exist. It does not exist. Now, just a note, had you picked, I'm just going to say, let me say down here. Had you picked R2 to be something like just the swapped of R1, so let's say, T0, you would still get 0. So that's what I meant to say. That's just a motivation that sometimes different paths might still give you the same answer. But if the question is to prove that the limit does not exist, you actually have to find a path that gives you a different answer than the limit of the previous path. For question 3, we are asked to work out the directional derivative of a function at a point in the direction of another point. So if we look at the definition of a directional derivative, we need a unit vector, and this unit vector needs to go from one point, in our case AB, to another point U. So that unit vector has to not only be in a specific direction, it has to be a unit vector. So the first thing we need to do is to get the direction vector from P in the direction of Q, which we denote by PQ with a bar on top. And that is just equal to the vector 3, 2 minus the vector 0, minus 2. And this will be equal to 3, 4. Now, as you can see, this is not a unit vector, and for a directional derivative, we need a unit vector specifically. So what we're going to do is we're going to find the norm of this vector, and this is equal to the square root of 3 squared plus the square root plus 4 squared, and this is the square root of 25, which is equal to 5. So this is the distance of this vector. So to make it a unit vector, we will just divide by its norm. So now we can call it U, which will be equal to 3 over 5 and 4 over 5. And this is a unit direction vector. It's just what I call it. Now we can apply the definition of a directional derivative, which tells us that d sub u of f at a point, the point 0 minus 2, is equal to the limit as h approaches 0 of f 0 plus 3 over 5h minus 2 plus 4 over 5h minus the function at the point 0 minus 2 over h. Now we're just going to substitute in. Now I know the function has an alpha in. I'm just going to leave the alpha. For your specific one, you can substitute in your alpha value. It's just going to be a constant. So then we have the limit as h approaches 0, alpha plus 1, 3 over 5h, plus negative 2 plus 4 over 5h, minus 2 over h. Now these two will cancel out, as this one will become, as this will become positive, it will cancel out. So we'll be just left with the limit as h approaches 0, alpha plus 1, 3 over 5. I'm going to take the h out to the front, factor it out, and then we're going to have plus 4 over 5, and this is over h, so the 8's cancel, so I just have the limit of a constant, which is equal to a constant. So we'll just have this.